Okay guys, Northern Oklahoma College, this is College Algebra Math 1513, Chapter 4, Section 5 in your book. And we're going to take all of our logarithm knowledge and put it together now to solve logarithmic equations. Alright, what does that mean? It means you're looking for the necessary exponent. Alright, you use logarithms when you're looking for an exponent. Alright, so something like this. I don't know what the exponent is. 5 to what power would give me 40? And it's going to be kind of an odd number. It's not going to be a whole number. It's not going to be nice and easy like, 5 cubed is 125. Well, that's kind of easy to guess. This one isn't so easy to guess. We're actually going to have to calculate it, and it's going to be a little messy. So our first step, since we have an unknown exponent, is to take the logarithm of both sides, or take the log of both sides. So all I'm going to do is just abbreviate logarithm and call it log, and apply that to both sides. Whatever you do to one side of the equation, you have to do to the other side of the equation to keep everything balanced. Okay, next I'm going to use my power trick, my power property, to move that exponent to the front. And we have this now. Now you guys remember we are multiplying here. We moved that exponent x to the front, and now it's multiplication, x times log 5. Well, how do I get the x alone? I just divide that log 5 off. Now remember, you have to do it to both sides. Keep everything balanced. My log 5 is gone. My x is isolated, so there we go. Our exponent, that missing exponent that we were looking for, that x, it's alone now. And all I have to do is plug log 40 divided by log 5 into my calculator and get an exact answer. And we get x equals 2.292. Whoops, I missed a 2. There's another 2 in there. 2.292029674 ... goes on forever. Rounded, it's about 2.29. Technically, this is inexact, all right, because we rounded. We rounded a lot of numbers off. Now, it's a good solution. It'll work. But if you want the exact answer, we would leave it in log form like that, log 40 over log 5. We're expressing the answer exactly. If we go ahead and take it to a decimal and round it a little bit, now it's inexact, but it's still pretty good. All right, let's check our answer real quick. Let's take our original equation, 5 to the x, and we're saying x is about 2.292029, and it's supposed to give us 40. Let's just check that in the calculator. Grab your calculator and put in 5 and raise it to the 2.292 power. And you'll get 39.999, something like that, which is pretty darn close to 40, okay? This is what we get because we were using an inexact answer, the 2.292, the rounded answer. So we're a little bit off, but you see it's close enough to be useful. Now, you don't always have to use a logarithm. You want to use it when it's necessary. Sometimes you can just use powers of numbers to solve a problem. For example, I'm looking at this one, and I could solve it with logs. We already know how to do that. Or I could recognize that 9 and 243 are both powers of 3. 9 is 3 squared. So I can replace the 9 with 3 squared. And then 243 is 3 to the 5th power. So I'll replace the 243 with 3 to the 5th power. And then I'll just kind of juggle these around, raising 3 to the 2nd power and then to the x power. I multiply those exponents and get 2x. So 3 to the 2x equals, now 3 to the 5th is on bottom. If I move it to the top, all I have to do is make the exponent negative. All right, negative exponents, just flip it to the other side of the fraction. So 1 over 3 to the 5th is the same thing as 3 to the negative 5 over 1. Flipping it just makes your exponent opposite sign, and 3 to the negative 5 over 1 is simply 3 to the negative 5. Now, since our 3's are equal to each other, it makes sense that our exponents must be equal to each other. That's just logical, all right? It's an equation. If our 3's match up, our exponents must match up. So set them equal to each other and solve, and you get negative 5 over 2 must be our exponent, and we do it without logarithms. So you have to decide when to use logarithms. Sometimes it's easier if you just use powers and exponents like I did here. I'm going to go ahead and work it with logarithms just to show you that you can work it both ways. Alright, so take the log of both sides, move your exponent x up to the front, that's that power property, and divide both sides by log 9. and your calculator will do the rest. You just have to be careful about your parentheses. Just watch your parentheses as you put it in the calculator. It should come out negative 2.5, which is the same thing as negative 5 over 2. Either one of those is correct. All right, and of course they're going to get a little trickier. Here's one. Look at the exponent. There's an x in it, so we're looking for an exponent. Now, what do you use? What do you use when you're looking for an exponent? When you don't know what the exponent is, you use a logarithm. So take the log of both sides. You always use a logarithm when you're looking for an unknown exponent. And then let's apply that power property and move the exponent. Now notice the exponent is this whole expression here. I'm going to move that whole expression to the front as multiplication. Now if I write it like this, it looks like just the x is being multiplied by the log 10. I want to make sure I put parentheses around it to show that the whole exponent, the whole 6 minus x, is multiplied by the log 10. And over here we have log 550. And you guys probably guessed the next step is to divide that log 10 off. All right, and I could put log 550 over log 10 into my calculator, but it would go to one of those nasty long decimals, and I just don't want to deal with that right now. So let's just leave it in log format right now. Now something you kind of need to be able to spot is stuff like this right here. That's a real simple log when you think about it. Remember, our base is 10. It's a common log. So we're asking ourselves, okay, that base of 10 raised to what exponent would give me that answer of 10? Well, think about it. 10 has an exponent of 1. That's an equation. My 10s match up. Therefore, it makes common sense that my exponents match up. So my exponent must be 1. So I can evaluate this log in my head. I can say, okay, log 10, what exponent would I need to put on that 10 to get a 10? That would just be a 1. So I'm going to replace this whole expression here with a 1. So I get this simplified one step further. Now at this point, I see this negative x right here. And what I'm going to do is, technically, I'm going to add x to both sides. I don't like negative x's. I want to make it positive. So I'm going to add x to both sides. Or another way to think about it is I'm just going to take this negative x and move it to the other side. And when I move it to the other side of the equal sign, it becomes positive. So I have this now, 6 equals x plus log 550. I want to get the x alone, so I'm just going to minus that log 50 from both sides. So I get x, my exponent, needs to be 6 minus log 550. All right, that's my exact answer. Now if I go ahead and plug the log into my calculator and do 6 minus log 550 in my calculator, I can get one of those nasty decimals, and you think that's the exact answer, but actually you're going to have to round off a little bit of that, so it'll be just a tiny bit off. So since the book asks for an exact answer on this problem, I'm going to leave it in log form, 6 minus log 550, so that technically on paper I have the exact answer. It's okay to change it to the decimal form, but just realize that the decimal form is inexact because you're cutting off some of that repeating decimal. All right, here's another example. Of course, it's going to get trickier and trickier. We don't know what the exponents are, so we have to use a logarithm. Now, the book used a natural log for this one, and it doesn't matter. You can use a log or a natural log. They're both logarithms. Natural logs just have a base of e, and common logs have a base of 10. It doesn't matter which one you use. So, yeah, we'll use natural log. It works either way. All the power properties and all those properties apply. All right, I'm going to move those exponents to the front. That's our power property. And remember, we have to be careful because it looks just like the 2 is being multiplied by the natural log 3. Actually, I want the whole exponent multiplied by natural log 3. Same thing over here. It looks like natural log 4 is just being multiplied by the 1, but I want it multiplied by the whole exponent, 2x plus 1. So use parentheses. Now, the next step is, you guys remember that natural log 3, that's just a decimal. All right, it's just a number. We can put it in our calculator, and we'll get this weird decimal number. But I don't want to do that right now because I don't want to write that decimal number. So I'm going to leave it natural log 3. But look at what's happening here. I have a number, a decimal number, multiplied by x minus 2. Well, that's just the distributive property. So I'm going to distribute the natural log 3. I'm going to multiply each one of those things in parentheses by the natural log. And I'm going to do the same thing over here. Natural log 4 times the 2x and natural log 4 times the 1. Okay? just put those numbers in front of the natural log and we'll be fine. So x times natural log 3 is just x natural log 3 minus 2 times the natural log 3. So I just distributed the natural log 3 to both the x and the negative 2. Over here I have 2x natural log 4 plus, and now multiply the 1 times natural log 4. Well, 1 times natural log 4, that's just natural log 4. All right, remember we're trying to get the x's alone. So right now they're on separate sides of the equal sign, so we need to gather them on one side. I'm going to do it by minus and 2x natural log 4 from both sides. Now at the same time, since I want the x's to be alone over here, I'm going to get rid of that 2 natural log 3 by adding 2 natural log 3 to both sides. We'll just do it all at once. We'll move the 2x natural log 4 and we'll move the 2 natural log 3 at the same time. And here's what we have. Now notice we have an x in common over here, so I'm just going to factor that out. So there I factored out the x. Alright, now remember I want to get the x alone. Remember what's happening over here. The x is being multiplied by that group in parentheses. So I'm just going to divide that whole group off. Just like that. And so our final answer is just this expression over here. Now I could put that in my calculator and get this nasty decimal, but that would be a little bit inexact. And since they asked for an exact answer, I'm going to leave it in log form. And we wind up with that. That will be our exponent. Once you change that to a nasty decimal, that's the exponent you would put in to make that equation work. All right, what if you see an e? Well, with an e, you're always going to use a natural log. Anytime you see an e and you're looking for an exponent, you're going to apply a natural log to both sides. So take the natural log of both sides, move that exponent to the front. Remember to use your parentheses because we're multiplying natural log e times that whole thing. All right, remember natural log e, that is just a number. So I can apply the distributive property, and I could multiply this out like this if I wanted to. All right, another thing I can do is that since this is just multiplication and I'm trying to get the x alone, well heck, let's just divide that natural log e off. And I have x plus 1 equals natural log 20 over natural log e. Now, we got to stop here. This is one of these things you got to start trying to recognize. Natural log e is one that we can calculate in our head. So think, natural log e equals what? Think about it like this. Natural log of e equals x. Now what's the base on the natural log? The base of a natural log is e. So I'm asking myself, e raised to the x power would be e. And I'm thinking, well, what's the exponent there? That's just a 1. Now since my e's match up, my exponents must match up. Therefore x must be 1, which makes perfect sense. E raised to the first power gives us e. So I'm going to replace this whole expression here with the number 1. So we have x plus 1 equals natural log 20 over 1. Well, dividing by 1 doesn't do anything, so I have x plus 1 equals natural log 20. And I'm going to minus that 1 off. And x equals natural log 20 minus 1. All right, so good thing to put in your notes is the natural log of e equals 1. We just figured that out. Another good thing to put in your notes is the natural log of 10 also equals 1. Because remember, the base on the natural log is e, and e to the first power is e. That makes sense. And the base on a common log is 10. And 10 to the first power equals 10. So that makes sense. So these are two good things to put in your notes and start looking for on the quizzes and homework. Okay, one more I'm going to try and do real quick is, what if you see this right here where they have some logs mixed in? Well, let's try and get our logs on one side of the equation. It's the same thing as trying to get your x's on one side of the equation. All right, now remember your log properties. We're going to change subtraction to division. And now think, that's log base 10. Let's take it back to exponent form. And now we just solve this using algebra. I'm going to cross multiply and put the x's together. And there's our exact answer.